it also give us a prior edge. Here we can able to identify that yes, these three factors has more synergic effect, or these are more prominent in these hydrogen and playing more role. Like if monomer is playing major role in the synthesis, or it's a cross linker that plays a major role for its synthesis. So this RSM is nowadays, through RSM we can also mathematically prove as well as optimize our parameters. So this is actually the attempt in one of my work where we have synthesized the hydrogel on a nanoscale. We are able to synthesize the hydrogel in the form of a nanospike. So here we have used the guar gum. Guar gum is actually a gum that is actually a very good emulsifier, and it is a very good food additive also. Most of food products contain this guar gum, and it is actually a very good emulsifier also and additive also in many of the processes. So here, as we can see in this particular, if you are able to see, so here the initiation is through the breakage of ammonium persulfate, which we have used here as a initiator. So it gives us a sulfate ion, and in next to it, because we are using the water, so water also get break down in the presence of it, and you produce the hydroxyl ion radical. So these radicals are actually initiate the course of reaction, and later on they activate the active sites on our backbone, that is actually a gum, as well as on the monomer, and then leads to the propagation. Then this propagated molecule, because they are in an activated form, when they come close to each other, then it leads to only the termination. So this is actually how the reaction takes place, and how it leads to the formation of hydrogen. And this, as you see in images, in the last image of that is E, basically very beautiful spikes, a nano that is actually in the range of 1 to 100 nanometer. We are able to get it. And this particular hydrogel turned into a very good material for removal of dye, because it has a very good capacity to remove the dye from the water. So we have studied the different effects of initiator, time, solvent on its preparation, and we observed that if we increase the initiator doses, as whether it's in the solvent, the solvent is also partially gives us a initiator. So if we totally increase it, there is a excess of generation of free radicals, so that leads to a premature decaying of reaction. So we need to have an optimized dose of everything. So by optimizing these factors, we are able to understand that what are the basic good things for its preparation. So from here, we got, and my team, my students, we got an idea of why don't we solve the problem through this hydrogen. Why don't we turn this hydrogen into a film, or into something that can be a very potential replacement of plastic, like plastic or the aluminium foil. This aluminium foil is a very common material which we use to wrap up the food material. And one thing is that, like, we use a packet of a Maggi or a chips, we eat it and then we throw it. And we don't even care for its fate, Like if the first synthesized plastic, that is in 19th, it is still on our earth, because it takes 1000 years for integration. So that is the motive for this work, and luckily just a month ago we got patent for it. So this is the invention where we have used the green material. It's again through the hydrogen, where we use the gum neem, a potential material for its synthesis, and a emulsifier that actually provided a plasticity, so that we need not to use the any material that will be increase its plasticity, any commercial material or a chemical for it. So we have used a nano-ionic surfactant, which is actually a emulsifier, but it give a very good stretching to it. We use the hydroxyapatite, which is actually a component of enamel in the tooth. We prepared it into the lab, and then we use this material. And later on we find out that it gives a very good, when it's prepared, it is a very good replacement to plastic, and it gets degraded in 12 to 15 days in earth. And when we check its solubility, it is completely disintegrated, soluble in 30 days in normal water. In saline water or sea water, it gets disintegrated in 25 days. And when we check its toxicity, in vitro cytotoxicity over the cell line, that is the FR2, a normal breast cell line, we observe no toxicity. And the best thing is that it enhances the shelf life of food products for more than 7 to 10 days. This is actually a tentative scheme of this invention where we have used a seaweed based material, then we add the hydroxyapatite at a particular at a particular RPM speed, then after the sonication and through a microwaving it by a simple casting method, we are able to get the best nicely formed film, which we can able to turn it into a packets as well as into a glasses, so that it will be turned to be a very good material for that. And this is actually just images that are showing that how we have just, when we put it, we observe that in 30 days it is completely disintegrated, completely gets solubilized. In 30 days in normal water, in lab testing 25 in saline water and in sea water as well. When we check it over the fruits, we have take a temperature of 29 degrees centigrade, and at that temperature we put some fruits into this particular foil and some in the plastic. We observe that the fruits we have packed in our foil, it increased the shelf life of that for more than 7 days. Similarly, on the fruit itself, another fruit, this is just a trial images. This is how we thought that yes, this can be a potential. Then another idea struck to the mind that why won't we use it for a field study, to be used on an agriculture point of view. So at that time we have designed a model that for the synthesis from a gellan gum. Gellan gum is a very common gum that is actually present in the native areas of Punjab, very commonly found gum. And people are using it for the sometimes just in Ayurvedic purposes, to take it to cure the stomach ache, etc. Nothing more it has been done with this gellan gum. So we have prepared it, and then we observe that it is actually when we prepare the tablets from it, a material from it, and we study it in a burial soil, simple garden soil, and into a vermicompost soil, we observe that it has a very good capacity. It holds 1,000 times more than its original weight, and it releases the water very slowly. So it reduced the irrigation frequency for more than 10 days. It eventually, with the passage of a time, slowly it releases the temperature. And we have also observed that when bacteria and other things, they can able to break down it because it's a completely biodegradable. At the end of its cycle, it is completely get disintegrated. And in vermicompost, we observe that yes, it is more easily it get completely out from the system without causing any effect. So it, at the end of it, it also increased the fertilization capacity of the soil. So from here we got an idea that why won't we again put a patent where we provide a 5-in-1 solution: nitrogen, phosphorus and potassium based superabsorbent material that not only give the nitrogen, phosphorus and potassium, but also hold the moisture, and at the end it increases the fertility. So for this particular thing, we have used a gelatin. Gelatin is again a gummy-like material, so which we get from the algae, water algae. So we took it and through a reaction with urea and that potassium diphosphate, we added the potassium, we added the component like nitrogen, phosphorus and potassium into it. And then when this material gets ready, we have incorporated, for this another thing is that we also wanted a very much super absorbent or something that absorb a huge amount of water. Next please. For that particular thing, we have used the guar gum, and then we fuse both the material together, and then it will comes out a NPK based fertilizer at the end. Because that material gets interpenetrating into it during the synthesis process, and then it will be turned out to be an NPK based material. Then when we took this material, we took the 3 very much utilized fertilizers in Punjab region. We took the three most selling hydrogel based materials, and we take a particularly initially a lab study. Now it's under the study of Punjab University Agriculture Department. So we just when we take it in the first, as you see in this particular image, in the first A pot, we just add simple the nitrogen for simple chemical. In the three and four, in the four we added the fertilizer, which we actually get the commercial, and then we take the three major type of different plants which are actually grown into that particular season. And in the last, we have used a fertilizer that we have prepared. And when we conducted this study for more than 40 days, 30 to 40 days, and we observed that not only the this need of irrigation reduced, but the shoot growth, the root growth, everything, we get more and more, the quality of vegetation is also improved in all the three cultivated things. So this is actually the study. Like we have observed that the shoot growth is very good, root growth is very good, and then eventually when we apply for a patent, and then eventually the PU, because at that time I am a postdoctoral fellow in Punjab University, so they opted it and they use it for the actually a large study in the village area, or in sometime the university has their own area. So, but it passed all the tests and it comes out to a very good fertilizer. Then we thought that we have to put it for the next thing for patent process. So these are generally actually some of results which we observe in the form of shoot, root, lens, their fresh mass, their dry mass, just like this. So after this, again, an emerging thing, that is a global water problem is there. Like we know that 54% of India is facing the high or extremely water stress nowadays, and 6% of our GDP is directly going just to purify the water. So it is essential to talk about the treatment strategies out of it. So when we see when we as a team saw all these things, we thought that yes, the replacement or the water purification option must be like this, that it should be highly effective, eco-friendly, and low cost absorbent should be there. So for this, then we thought that yes, because we know that hydrogel have that capacity that they remove the dye from the water. But then one another idea struck to it, that why won't we use it as a oil absorbent or a diesel absorbent also for actually removal from the oil spillage in the sea areas. So initially in the first work we have choose the gum gelin, and for this study, and here we have employed it for the removal of methylene blue and methylene from guargan from methylene blue and malachite blue. And we observe that at very low pH, yes, it turns to be a less effective, but as the pH gets raised, it turns to be a very good material for its absorption. Sometimes it gives us a very like pseudo first order. Sometimes it shows a dependency of one of the reactant. Yes, this is the major who is actually playing good for its absorption. Sometimes it's showing us a second order from our linear regression model. But the results are quite good. But it is able to absorb dye within 4 to 5 hours and very efficiently, and we are able to reduce it out. We are able to reuse one material many times, reusability of 10 to 12 times we can able to make from this material. As you see in the pictures, like after the 5 hour of incubation and shaking, the 100 ppm is reduced to 4.47 ppm, and we can able to reduce the this gum out completely out of the hydrogel, and then we again reuse 10 times, and it is effectively for all those 10 times they are actually removing the dye from it. So as you see in this picture, so why methylene? Because this particular material, because of the presence of with acrylic acid over it, it has a chain of carboxylic CO bonds or OH bonds. The groups are there, so they are act as a very effective bonds where there is an attachment of dye can happen. So a dye get attached to its surface, and because hydrogel have a very wide surface, so they can eventually able to absorb much amount of dye to it. And then we can, by simple washing, we can able to reduce that dye out of it, and again able to reuse for many times from by the way of swelling, de-swelling status. So from here I have put an project to Ministry of Small, Medium, Large Enterprises, and for the design of a cost-effective reusable hydrogel-based superabsorbent for water filtration. So this is actually for the rural area. My thinking is that we should provide a very reusable and efficient water purifier for the rural area, and MSMA also give me a grant of 15 lakhs for it, and we are actually in the process of now making it, because this is again with the incubation center of Punjab University. So then one more thing, as I am talking to you, that effective oil spillage, because oil is something that we need to take up from the surface of the water. As when we are talking about, yes, we need to clean our seas. So for this particular thing, one of the biggest challenges, because hydrogens are hydrophilic material, and we need to turn them, we need to make them a hydrophobic type of thing. For that particular, after studying for many days, we come across an idea that we can use a octadecyl trichlorosilane, because these are the silane material, and silane material they are hydrophobic in nature. So the major challenge is that use of this particular thing, and just to imbibe them into a hydrogel and to make actually hydrogel out of it. So by a simple de-coating method that we have employed at a room temperature, so we then use this material over a methacrylate based hydrogel for its study. So it provides a very good floatability and hydrophobicity to the material. So in the image, you can able to see that when we put it into a beaker, it don't take even a single drop of water. But as soon as it comes in a contact of a oil, whether it's oil, is any of the oleophilic thing, is maybe it's a part of a diesel or something. So it eventually get those material, these oils get attracted towards the hydrogen, this hydrophobic hydrogen, and get into it completely. It soak up the oil, but it won't take a drop of hydrogen. And best thing is that it is able to float over the surface because of its hydrophobicity, because of the presence of this OTS material. Yes, as you see in the picture, as soon as we put a drop of oil, obviously we dyed it with red dye so that we can able to see the changes. So what we observe that as soon as we are putting a drop, eventually it get attracted towards and it absorbs. And best part of this material is that we can able to reduce that oil out of it, and then we can use it many times. Reusability is also we can expect it from this material. It gives a very good result. When we go for its SEM images, what we observe that this OTS modified hydrogel have a very good pore size, that porosity is there, and when we go for a contact angle study, yes, we observe that by optimizing its amount, the contact angle between the oil and the hydrogel, OTS based hydrogel, is increased eventually. So this is because of that force that actually have on its surface because of this OTS material. Then we employed the curcumin again. We thought that why won't we prepare some of the antibacterial agents, because at that time COVID is also there and everybody is talking about anti-viral things or antibacterial things, and even the hospital people are suffering from the infection of E. coli, a normal UTI infection. So we thought, why don't we use a curcumin? Curcumin is simple haldi that we are actually using in our homes as well. So we actually synthesize a curcumin loaded a butyroscomis based hydrogen, and this also turned to be a very efficient antibacterial agent. we have synthesized again through RSM. We see the synergic effect of many factors, and we observe that the monomer concentration and the cross-linker concentration are playing a very important role for its synthesis. And when we studied it over different bacteria like E. coli